Look at your hand for a moment. The carbon atoms in your skin, the iron in your blood, the oxygen you're breathing right now. None of it was created on Earth. Every single one of those atoms was forged inside a star, then violently ejected across the galaxy when that star exploded. Until recently, we couldn't ask the specific questions: which star, which explosion, what path did your atoms take through the galaxy? The resolution in our simulations just wasn't there. To answer these questions, you'd need to simulate the entire history of our galaxy. Every star, every explosion, every atom scattered across 13 billion years. You'd need to track hundreds of billions of stars simultaneously, watching how they live, die, and seed the galaxy with the building blocks of life. For the last 50 years, this was considered impossible. The computational power required was so staggering that scientists called it the billion-particle barrier, a wall no supercomputer could break through. Until November 2024, when a team in Japan did exactly that. My name's Max, and you're watching Quantum Reach. Today, we're investigating how scientists can now trace the history of elements through our galaxy, and why understanding this cosmic recycling reveals how planets like Earth became possible in the first place. Our galaxy is an immense structure, approximately 100 billion stars, all orbiting a common center over hundreds of millions of years. Throughout that history, massive stars have been exploding as supernovas, blasting heavy elements into space. Those elements mix with gas clouds, condense into new stars, and eventually form planets like our own. This is cosmic recycling on the grandest scale. The iron core of Earth was forged in stars that died before our sun was born. The calcium in your bones was created in supernova explosions billions of years ago. We are, quite literally, assembled from stellar debris. Scientists would like to know more about the exact path. Which generation of stars created which elements? How supernovas distributed material across the galaxy? And when gas clouds accumulated the right mixture to make rocky planets possible. To answer these questions, you need a simulation detailed enough and with enough resolution to track individual stars. And that's where things get tough. In a galaxy simulation, every single star gravitationally influences every other star. For 100 billion stars, you need to calculate roughly 5,000 billion gravitational interactions per time step. And you need millions of time steps to simulate just 1,000 years of galactic time. The maths is absolutely brutal. Previous simulations could handle maybe 1 billion particles, but each particle had to represent about 100 stars lumped together. It's like trying to understand human genealogy by tracking cities instead of families. You can get a broad picture, but you lose the details that matter. Kaiya Hiroshima, a researcher at RIKEN's Center for Interdisciplinary Theoretical and Mathematical Sciences, knew exactly what the problem was, and it wasn't just the sheer number of stars. It was time. Galaxies evolve over billions of years. This is called the simulation timeframe. But supernovas, the explosions that seed the galaxy with heavy elements, happen fast, very fast. A star collapses in seconds, the shockwave bursts through the surface in hours, then the ejected gas expands and cools over the next 100,000 years. To accurately simulate that gas expansion, you need tiny time steps, small enough to capture the rapid changes occurring in the heart of a supernova explosion. Run those tiny time steps for 1 million years of galaxy time, and you're looking at 315 hours on a supercomputer, more than 2 straight weeks of computing. To simulate 1 billion years, the timescale meaningful for galactic evolution, would take 36 years. No research team can wait that long, and no supercomputer can be reserved for that duration. And so, the billion-particle barrier stood unbroken. Scientists could either simulate lots of stars crudely or a few stars precisely, but not both. The cosmic genealogy of our atoms and the atoms that make up the world around us remained out of reach. That was until Hiroshima and his collaborators at the University of Tokyo and Universitat de Barcelona asked a different question. What if we didn't have to calculate everything? The team's insight was elegant. The reason simulating supernovas takes so long is that you need to track how the ejected gas behaves, how it expands, cools, and eventually disperses into the surrounding galaxy. But that process, while complex, is governed by well-understood physics. After a star explodes, the gas evolution follows predictable patterns. Given the initial conditions, the energy of the explosion, the density of surrounding gas, and the composition of the ejected material, you can, in principle, calculate what the gas will look like 100,000 years later. But, in principle and in practice are very different things. The calculations are extremely expensive, and that's the whole problem. So Hiroshima's team did something clever. They ran hundreds of high-resolution supernova simulations for full physics with tiny time steps and full computational power. Then, they trained a deep learning model on the results, teaching it to recognize the patterns in the gas and predict the outcomes. Eventually, the AI learned to predict what would happen. Given the initial conditions of a supernova, it could forecast the gas distribution 100,000 years into the future. Not by calculating every time step, but by pattern recognition, the same way you can predict where a thrown ball will land without solving the equations of motion in your head. Next, they built a hybrid system. The main galactic simulation runs normally, tracking stars through space and calculating their gravitational interactions. But whenever a star explodes, and in a galaxy like ours, massive stars detonate a supernova every few decades, the simulation hands over the calculation of that explosion to the AI. The AI can then predict the gas evolution over the next 100,000 years, feeding that information back into the main simulation without needing tiny time steps or hitting the computational bottleneck. What used to take 315 hours per million years of galaxy time now took only 2.7 hours. They'd achieved roughly 100 times speedup. Suddenly, simulating a billion years wasn't a 36-year project, it took only 115 days. This is still a substantial amount of time, but of course much more feasible. In November of 2024, they ran the simulation on Fugaku, one of the world's most powerful supercomputers. Located in Kobe, Japan, Fugaku has 158,976 compute nodes and 7 million processor cores. And Hiroshima's team took advantage of much of that power. What emerged wasn't just impressive technically, it was the first time humans had ever watched an entire Milky Way-scale galaxy evolve star by star, tracking over 100 billion individual objects through 10,000 years of history. But it wasn't just the speed that was impressive, it was the resolution at which the simulation could run. Hiroshima's simulation tracks every star individually. At this level of detail, you can even trace the origin of specific materials, the exact supernova that contributed iron to the Earth's core, or which stellar generation seeded the gas clouds that became our solar system. When a massive star reaches the end of its life, its core becomes layered like an onion. Hydrogen and helium on the outside, but deeper down, carbon, oxygen, silicon, and at the very center, iron. These elements are created through nuclear fusion, with stars acting as cosmic forges for heavy elements. When the star explodes, those layers are blasted into space. The iron from the core, the oxygen from the surrounding shells, all of it becomes part of the interstellar medium. Over millions of years, gravity pulls that enriched gas together with other clouds, and eventually a new generation of stars form, this time containing carbon, oxygen, and iron, alongside the hydrogen and helium. Our Sun is at least a third-generation star, maybe more. The heavy elements it contains, and that the Earth inherited, came from stars that lived and died long before our solar system even existed. But we want to know which stars, and that's something we've never been able to answer precisely. Now, for the first time, we can trace it. Hiroshima's simulation tracks where every supernova's material goes. It shows how heavy elements spread through the galaxy, which gas clouds become enriched with which elements, and when new stars form from that enriched material. This allows us to trace the lineage of planets and suns with actual precision, showing this oxygen atom was created in that specific supernova 8 billion years ago, traveled here, mixed with this gas cloud, and eventually became part of the Earth's atmosphere. The simulation Hiroshima's team created is, in a very real sense, a time machine. It lets us replay our galaxy's history and watch how the elements that make up everything we know, including ourselves, were forged and distributed across space and time. And that's why breaking the billion-particle barrier matters. Not because it's computationally impressive, although it is, but because it finally gives us the resolution to understand our origins at the deepest levels. There's something profound about being able to track individual stars rather than lumped clusters. Previous simulations could show you how spiral arms form or how galaxies interact and merge. Those are important questions. But they couldn't tell you why Earth has the precise mixture of elements it does. They couldn't explain why life-essential elements like carbon and oxygen are abundant enough to form complex molecules, but rare enough that rocky planets don't just turn into giant carbon or oxygen worlds. Hiroshima's simulation can answer those questions, and the answers are already surprising. The team found that element enrichment across the galaxy isn't uniform. There are regions where iron-rich gas from multiple supernovas accumulated, creating pockets where planet formation could produce more massive iron cores. There are other regions where carbon and oxygen dominate. The simulation also revealed how star formation rates changed over time as the galaxy became more enriched with heavy elements. Early generations of stars were almost pure hydrogen and helium. They couldn't form rocky planets at all. But each generation enriched the galaxy further, until eventually stars like our Sun formed, with enough heavy elements in their protoplanetary disks to create Earth-like worlds. Hiroshima and his collaborators realized something else. This hybrid approach, combining physics-based simulation with AI-predicted outcomes for the expensive parts, isn't just useful for galaxies. As Hiroshima himself put it, this work marks a fundamental shift in how we tackle multi-scale, multi-physics problems across the computational sciences. Take climate modeling, for instance. You've got small-scale processes, individual storm cells, cloud formation, turbulence, and large-scale processes, global atmospheric circulation, ocean currents, jet streams. It's the same problem galaxies have. Small, fast events embedded in slow, large systems. Current climate models have to make compromises. They can either run high-resolution simulations of small regions or low-resolution simulations of the whole planet. Getting both has been computationally prohibitive and impossible for the last few decades. But if an AI can learn to predict how supernova gas evolves, it can learn to predict how storm systems evolve or how ocean eddies disperse heat. The same hybrid approach could dramatically improve climate predictions while reducing computational costs. Or we could consider fusion energy, one of humanity's best hopes for clean, abundant power. Inside a fusion reactor, you've got plasma physics happening at multiple scales simultaneously. Atomic-level interactions determine how particles behave, but you need to model the entire reactor to understand stability and efficiency. Right now, fusion simulations are limited by the same barriers galaxy simulations faced, but the hybrid approach could change that, potentially accelerating the development of practical fusion reactors by letting scientists test more designs more quickly. Again, we could see the same principle applied to the material sciences and drug design. Anywhere you have processes happening to vastly different timescales, from femtoseconds to years. This hybrid AI physics approach could break through computational barriers that have limited scientific progress for decades. Hiroshima's team isn't stopping with their first success. They're already working on the next generation of the simulation. They want to include cosmic radiation effects, model black hole accretion in galactic centers, account for magnetic fields threading through interstellar gas, and track chemical evolution in even finer detail. Eventually, they hope to simulate not just 10,000 years, but the entire 13 billion year history of a Milky Way-like galaxy, from its formation in the early universe to the present day. They want to watch how the first stars formed from pristine hydrogen and helium, how those stars exploded and enriched the gas, and how generation after generation of stars built up the heavy element abundance that eventually made our planets and life possible. If they can do that, we'll be able to test theories about galactic evolution in unprecedented detail. We'll understand how galaxies like ours became stable enough to form solar systems. We'll see whether our particular history was typical or unusual. And perhaps most remarkably, the team has announced plans to release their simulation framework publicly. That means researchers around the world, not just those with access to the most powerful supercomputers, will be able to run their own galaxy simulations. Similar to what happened with AlphaFold, the AI that solved protein folding. Before AlphaFold, determining a protein's structure took months or years of laboratory work. After AlphaFold made its model publicly available in 2021, anyone could predict protein structures in minutes. It democratized an entire field of research, accelerating drug discovery and our understanding of biology. Hiroshima's galaxy simulation could do the same for astrophysics, and for any field wrestling with multi-scale, multi-physics problems. So let's return to where we started. Your hand and the atoms in it. We've known for decades that those atoms were created in stars. Carl Sagan famously said, "We are made of star stuff," and he was absolutely right. But until now, we couldn't trace the specific paths those atoms took. What Hiroshima's team has created isn't the final answer. It's the tool that makes answering possible. They've simulated 10,000 years of galactic evolution at individual star resolution. For now, it's a proof of concept, but a profound one at that. The team's next goal is ambitious: to simulate the entire 13 billion year history of a galaxy like ours, from the first stars to the present, and if they succeed, we'll finally be able to trace the journey that the atoms that make up our planet, bodies, and everything around us took through the galaxy and the supernovas in which they originated. For 50 years, the billion-particle barrier has stood because scientists tried to outcompute an impossible problem. Hiroshima's team broke through by outthinking it, combining AI with physics to handle what neither could achieve alone. The simulation running on Fugaku isn't just a technological achievement. It's the first step towards answering one of the deepest questions we can ask. Where do we come from? The full answer isn't written yet, but for the first time, we have the pen. Thanks for watching. I'm Max, and this is Quantum Reach.